coefficients, how can you check the quality of the models and so on. Okay, but just let me recall you, because we have a really huge break, and let me recall you some theory that we discussed previous time. So for some students maybe who miss some classes, I want to say that now we are talking about not the ordinary least squares method. Since the previous lecture and during your last seminars, we talk about the maximum likelihood method and logit and probit models. We discussed many times that ordinary least squares method will work with the continuous dependent variables. For example, such as income, such as GDP per capita, and so on. But in real life, of course, when we conduct some research, we work not only with the continuous variables, we also work with the variables of a more discrete nature. And binary or dummy variable is a discrete variable, and when we face such kind of variable and want to include this variable as the dependent variable in our model, OS method will not be efficient. We discuss all the limitations why OS will not be the efficient method. You can check the previous slides of the lecture. So today we have to learn and review the intuition behind the maximum likelihood method. So we discussed previous time that when we use binary response models, such as logit or probit models, we can overcome problems with binary outcomes that we could face when we still want to use ordinary least squares method for some reasons. I don't know the reasons. And this is very simple, that now our dependent variable, it's describe the probability that y equals 1. In other term, we can say this is response probability that equals some function. Some function. What type of function could we put here? We took a look previous time that this function looks like a curve. Yeah, you remember, looks like a curve, and this is a cumulative distribution function. But what type of cumulative distribution function? We discussed that we have two options. The first option, we can say that this is cumulative distribution function of standard normal distribution. In this case, we use probit model, or if we say that this cumulative distribution of logistic function, we use logit model. So that was the main idea that we discussed in details previous time. And also we discussed, and also I think that the same discussion and the same you learned from the seminars, that you can't directly interpret the coefficients from logit and probit models. It's very difficult. We took a look. We are going to take a look why it's difficult, and you will see that this will be a problem. So before I just a second. Before I show you how can we apply maximum likelihood method to logit or probit model, let's start with the most simple example. Of course, MOE method, maximum likelihood method, comes from probability and statistic theory. It's a widely applied method even in the machine learning. So not only in statistics and in econometrics, this is general method for different tasks. If you will continue learning the machine learning classes, for example, I think that finally you will find the application. How can you apply this method even in such story? So the very basic idea that, let's say you have some pool, and in this pool you have red and yellow balls. Our main task, we want to understand the fraction of red balls in that pool. It's very easy. For example, if we have 20, let's say, first of all, we have small pool, and we have 20 or 30 or even 100 balls in some, and yellow, and red. In this case, you can take, for example, each ball and count. Take a look at each ball and count them, and find the fraction of red balls. But let's say that you have a really large pool that contains 1 million balls. Of course, you can follow the same procedure and manually count each ball, but it's not rational, and it will take a lot of time, and I think a lot of mistakes. So how can you do in this case? You need to find some solution for this task. And let's say that we take only a random sample of some number of balls, n. Here you can see, yeah? And don't look at all these balls. This is a classic example from probability theory, so we'll just need to discuss the idea of MOE on this example. And let's denote that our outcome variable y equals 1 if ball is red, and otherwise, or let's say equals 0, if ball is not red, or in other words, it's yellow. So also let's define n1 as the number of all red balls, and n minus n1 as the number of yellow balls. So you can note that this is Bernoulli random variable, yeah? And also, if you want to obtain the probability of such kind of sample, you can use this formula, yeah? I hope that you remember this from the probability and statistics course. So this is P, some probability, yeah, raised to the power n1 times 1 minus probability raised to the power n minus n1. And this expression we can interpret as a function of the unknown parameter p. Yeah, this is unknown parameter. And it's referred to a likelihood function. So generally speaking, the method of maximum likelihood estimation chooses values for parameter estimates which make the observed data, which make the observed red balls and yellow balls in that pool maximally likely. So what we just need to find, this is the unknown parameter, this one. And maximum likelihood estimation for P implies that we choose a value for P such the likelihood function. And if you find this estimator, you will find the answer on your question, in our case, the question about the fraction of red balls, but this is very, very simple example. Yeah, of course, when we conduct some regressions, we need to find more complicated relationships between the variables, and we need to estimate the probability of our outcome in more complicated way. This is just a simple example from the probability theory. And also, you need to remember that that was our expression, yeah? So how can we find the maximum? How can we maximize this function? How can we do this? We need to take the partial derivative, yeah? And also it's in the terms of calculus, in the terms of calculations, it will be difficult to work with such kind of expression. Here is the multiplication, yeah? Here is the product of two terms. And it's much easier to take the logarithm of both sides of this expression and to convert the product, the multiplication term, in the terms of summation. This is just for calculation simplicity. Okay, so if we take the logarithm of both sides of this expression, we obtain this likelihood function, log likelihood function. Now a log likelihood function, yeah, because we add the logarithm for calculations. Okay, what we want to find? We want to find this number. And when we maximizing this function, we get the first order condition. This all these terms is from math, is from probability, so all of them are known for you. Okay. What you need to do, you need to differentiate the log likelihood function with respect to the unknown parameter. In our case, in this example, this is p, and equate the resulting derivative to 0, and that's all. So when you solve the first order condition, you the solution gives the maximum likelihood estimate. This one, in this case, because we review very simple example. In this case, the maximum likelihood estimation equals this ratio. Okay. So the main idea that you should see from all these steps, that maximum likelihood estimator corresponds to the sample proportion of red balls and probably also correspond to your best guess for this unknown p parameter based on the sample that was drawn. Okay. So what else? Of course, to define the maximum likelihood estimator in, let's say, in more general situation, that in situation that are close for our task when we want to run the regression, yeah. In this case, when we want to find the relationship between the probability of some event occurs and the probability, it means the probability that our dependent variable equals 1 or equals 0, yeah. In this case, our interest lies in the conditional distribution of y given some x's, because we have some factors and we want to find how the change by 1 unit in one factor, yeah, influence the probability of getting the outcome variable equals 1 or equals 0. Yeah. So in this case, we can define the density or probability mass function be given by some function. And you can see here that we have our dependent variable as usual, our independent variables also as usual, yeah? But also we have some parameter, unknown parameter, theta. And also we need to assume that all the observations are mutually independent. What does it mean? For example, if we have in our sample different respondents, of course, we need to assume that all these respondents or all these firms, if we work with the sample of companies, are independent. As usual, yeah, we have the same assumption in the OS. And in this situation, uh, as we have many observations and we have many different density probability density functions, we need to combine them all together, yeah? And so, in other words, we need to find the joint probability mass function. Okay? How can we do this? If you remember, I hope that you remember that this sign is from Greek alphabet. P, yeah, means the multiplication. Yeah, means the. So, in other words, we combine all the individual probability mass functions in the joint density function. This, how can we know this? Okay. What we need to find in this case, we need to find this unknown theta parameter. And also we can rewrite this joint probability mass function in this way. Why we can do this? Because the likelihood function, this is very important. You need to understand that the likelihood function is just the joint probability distribution of the data. But we treat it with this function, we treat it with this as a function of some unknown parameter. We denote this here as theta, that help us to maximize the observed data set. Okay, the probability. I skip the word probability. Because of this, we can rewrite the same expression here. You can see this one, yeah, through the likelihood function. L here is abbreviated, means likelihood function, yeah, of some unknown parameter conditional on y, your dependent variable, and some x's. You know this. You know these factors, yeah? You can observe them from your data set. And again, you need to find the joint probability distribution. Because of this, you have here this sign, and it's better to remember about this every time, yeah, that this is joint probability distribution. This is easier, yeah? This is the function of a known parameter theta. And again, as we discussed here, if we want to maximize something, we need to find the first order condition. Yeah, and because of this, we need to take the partial derivative. But before we take the derivative, it's better to employ the likelihood contribution. Okay. In general terms, we can write all these ideas at the solution of this thing. So you need to maximize logarithm likelihood function of unknown parameter theta. Okay. And again, we need to solve the first order condition. This is abbreviation of first order condition. How can you do this? The same expressions, yeah? the same expression that you just have seen in the example about the blue and bow and red bows. And the first derivative can be found like this one. Do you remember why we need to take the second derivative after the first one? So if you need to prove that you have the maximum, uh, in this case, you can find the second order derivative, and this derivative will show that this indeed a maximum, not a minimum, okay? That easy idea what you need to do when you want to use the maximum likelihood method in general. But also you need to remember that as well as in ordinal least squares method, in the maximum likelihood method, you also need to find the variance because it's very important. Yeah, from the variance we obtain the standard errors, and when we obtain the standard errors, we can conduct the test statistic, we can construct the confidence intervals, we need to check the significance of our results. Yeah, because of this we need standard errors. And of course, in the asymptotic variance of the maximum likelihood estimator is given again from the Bernoulli distribution theory, and it's not the same. We can't use the same formula as in the ordinal least squares method. We use a different one, but the good news that as in the ordinal least squares method, the maximum likelihood estimator is distributed as normal according to the central limit theorem. And this is exactly what you can see here in the slide, that this is distributed according as normal. Um, and also this formula is I hope that it's known for you because you use the same formula when you want to test any hypothesis about your coefficients from the ordinal squares. The formula is the same, but here is you need to put here, if we continue our example about the red and yellow balls, here is the P. Yeah? And also after this, after you obtain the standard errors, you can find the confidence interval. If you want to find 95% confidence interval, you can use the same statistic value. And also you should remember, yeah, if you have a small sample, your confidence interval will be pretty large, but one of our goal, of course, we want to obtain efficient results. We want to obtain, we want to calculate the our parameters and the confidence intervals let's say very accurate. Yeah, and because of this, of course, we want that our confidence interval will not be large, will be rather small. And if you have a small sample, you can, let's say, sample of 100 balls, your confidence interval will be from 0.35, for example, yeah, to 0.54. But when you increase the sample, let's say now you have 1000 balls, and in this case, your confidence interval becomes smaller and narrow. Okay? And also, from this example, you can see that the normal distribution is an approximation based on large sample theory, and this approximation will never hold in small samples. Okay, you should remember about this. So now let's talk about the maximum likelihood estimation when we work with the logit or probit models. The logic is the same. Um, what are the difference? As we've just discussed, we follow the same steps as in the example with the pool and bows. But now we should plug in this general formula um, the specific value of this parameter p. Yeah, what does it mean? So the method of maximum likelihood consists in estimating the unknown parameter. But we need to estimate this parameter in such a manner that the probability of observing dataset, of observing outcomes of our dependent variable y will be as high as possible, or in other words, maximum. Because of this is the name of this method. Let's say that this task is very close to our research. Let's say that we want to find the probability that some individual, that some respondent owns a house. And we want to, let's say we use the simple regression and we have only one independent variable, explanatory variable, and this is individual's income. This is our X. So we need to make only one assumption. We need to make an assumption about the probability distribution of our error term. So if we assume that the probability distribution of the error term has a logistic distribution, in this case, we can write the function as the logistic function and use the logit model. We discussed this previous time. But if we assume that the probability distribution of the disturbance term follow their normal distribution, we will apply the probit model. Okay, and also you should remember that we don't actually observe this probability. Yeah, we only observe the outcome, the final outcome of our dependent variable. This variable can equal 1 or 0. 1 means that individual owns a house, and 0 if the individual doesn't own a house. And again, our variable follows the Bernoulli distribution. So we use the same formulas. Yeah, we use the same logic. And if we want to construct the joint probability distribution, we again use the same formula as we've just discussed. But now you should remember this is the general formula of joint probability distribution, yeah? But you can plug in here the logistic function instead of this um, in this general notation, okay? So after this, what again you need to do? You want to find the logarithm because we discussed this is the sake for simplicity, yeah? Before we want to find the maximum, we need to apply the, we need to, it's better to find the logarithm. Because of this, you find the logarithm likelihood function. So it's very easy to verify that after you derive this expression, you finally obtain this equation. And it's also, you can derive by yourself that it's easy to verify that instead of this expression, you can plug in here this one. And instead of this expression, you can plug in this one, because we work with the logistic distribution. Yeah, because of this, you can see here these expressions. And if you plug in here, instead of these general terms, the distribution of logistic function, yeah, finally, you can rewrite the logarithm of likelihood function as following. This will be your final model. So what you need to find? You can see that from this log likelihood function, you need to find the unknown parameters beta 1 and beta 2 in this example. Of course, if you have not the simple regression model, you can add here beta 3, beta 4, and so on. But in general terms, you need to find all these unknown betas, because X values are known. You observe them from your sample, yeah? When you find these unknown betas, this will be the answer. This will be the answer, and this will be the goal. How can you maximize the likelihood function? And that is the answer. How can you obtain the values of the unknown parameters in such a manner that the probability of observing the given dependent variable y will be as high as possible? And this is your main goal. Okay, so nice news and very pleasant news for you. Of course, the first news that you don't need to do this manually. It's not very simple to do this, of course, especially if you work with the probit models. It will be very hard to calculate all this manually. Because of this, all what you just need to understand this method and to correctly apply this method, correctly apply all your commands in our course. It will state a software, and of course you can use some other computer packages, software packages to run your models and to apply the maximum likelihood method. That's the first technical good news. The second one, that if you provided the likelihood function correctly and correctly specified your model, in this case, you obtain that the maximum likelihood estimator is consistent for the unknown parameter. What does it mean? It means that you have a probability limit of some estimated parameter theta, and it equals the true parameter in the population. Yeah, this is the same desired property that we want to obtain in the OAS, and also we want that our results will be consistent. Yeah, and also this is the same property that we can obtain if we correctly use if we correctly specify the likelihood function. Okay, the second very similar property of our estimates, that the estimator will be asymptotically efficient. What does it mean? Again, the same meaning as in the OS. It means that you have the smallest variance among all consistent asymptotically normal estimators. And also, the last one, that the maximum likelihood estimator is asymptotically normally distributed. Because of this, in the tables with the outcomes after the probit or logit models, you will see the very similar test statistic that tell you about the significance of each coefficient. And also you can construct the confidence intervals using this normal distribution assumption and check the significance. Okay, what else? Let's summarize the difference between the ordinary squares and the maximum likelihood method. Both of these methods are two, it's better to say not alternative methods, but this is just two different methods. How can we estimate the unknown parameters, beta, in our regressions? When you work with the very dependent variable that have such as categorical variables, such as binary variables, so the limited outcomes. In this case, ordinary least squared method is not a good choice, because ordinary least squares estimate the betas in such a manner that want to minimize the deviation between predicted and actual outcomes. You remember this is we discussed this formula a lot. This is very easy formula. How can we minimize this deviation? Yeah. But in maximum likelihood method, we use the other logic of how can we estimate them, our betas. In maximum likelihood method, we need to find our betas in such a manner that maximize the likelihood or likelihood function of the observed sample. Given the distributional assumption, maximizes likelihood function of unknown parameter betas, conditional on y and x. This is two different logic, two different approaches. How can we estimate our betas? Okay. And I hope that you understand in general what does it mean, but I also recommend you to read at home the chapter from the books that I recommended on the, you can find them on the last slide of this presentation. Please read them. You need more time, you need more time for reflection of this method, and you need, I think, more information if you don't understand the idea or you skip something. Okay, so please read more theory about the maximum likelihood method. Okay, so now let's talk about how can we interpret the results after the logit and probit models. So logit and probit models use the maximum likelihood method for finding beta parameters. And it's very important to measure the quantitative effect of change in our independent variable, let's say 1 unit increase in the independent variable, how this change affect the probability that we have in our dependent variable. Okay, this is our goal when we find the relationship between the two variables. So for this purpose, we use the marginal effects. marginal effects tell us how a dependent variable changes when a specific independent variable also changes. So we can define the marginal effect as a partial derivative with respect to x. So the derivative gives us the rate of change over the interval, which is very, very small. Yeah. And generally speaking, we have already learned how to find the marginal effects in the linear regression model, because we found them when we found the slope. This is the example of linear regression model when we use the ordinary squares method. Yeah, this is the general notation of this model. Then when we want to find how the 1 unit increase affect the change in our dependent variable, here is in this example, this dependent variable is continuous. Yeah, just want to remind you again that this is linear regression model. It means that you need to just estimate the beta 1 or beta 2, yeah, if we want to find the effect of the variable x2 on the dependent variable. Yeah. So in the linear regression model, the slope, this one, beta 1, yeah, or beta 2, so the slope measures the change in the average value of our dependent variable for 1 unit change in the value of regressor. This is how we interpret, yeah, our coefficients. And because of this, it was rather easier to run the regress command, to take a look at the betas, and to interpret the effect of change, to the effect of relationship between the two variables. We can do it straightforward, but in logit and probit models, unfortunately, we can't do this in the same way. Because in logit as well in the probit models, marginal effects, it means that we need to find the derivative, yeah, depends on the value of x. It means that they are not constant. So here you, in linear regression model, you obtain the constant effect of beta 1, of beta 2, and because of this, you find the average effect on y, on dependent variable. But if you remember, in logit and in product models, we have a probability curve. We don't have a line, we have a curve. And curve raises rapidly at first, then begin to increase at decreasing rate. Because of this, the slope is not constant. How can you understand this? Let's start with the logit model or logistic model. So you remember, if not, please check the previous lecture and the slides of the previous lecture. You remember that now, if you use the logit model, our dependent variable looks like this: a logarithm of some ratio, ratio that dependent variable equals 1 to the ratio that the dependent variable equals 0. Yep. And this is as usual. So when you estimate the coefficients from this regression, they are in the log odds scale. We name this ratio odds. Yeah, this is odd ratio. And it's very difficult to estimate, to interpret, sorry, to interpret in log odds ratio scales. What does it mean? It's hard to understand what does it mean exactly. It doesn't have any sense if you interpret that, for example, if you increase age by 1 year, it means that the logarithm of odds ratio of O in a house changed by some value. What does it mean? I don't know. And also, the most, if we try to interpret the probit model, this is the logit and this is the probit. In probit model, the dependent variable is some probability. Yeah, some probability that your dependent variable equals 1. For example, that the respondent owns a house, conditional on some characteristic like male, age, and so on, and income also, and so on. But on the right side here, you see a very strange function. Strange, I mean, in the terms of interpretation, strange. So the probit model is related to the standard normal probability distribution. And in the probit model, the rate of change in the probability is somewhat very complicated. You can see here is this. So in both cases, we have very similar problems. In logit and in probit model, I mean, it's very hard to interpret directly the beta parameters. Again, let me show you one more about that we just discussed. Yeah, so if you want to interpret the beta parameters straightforwardly, it will be very difficult because when you take a look at the probit model and when you take the partial derivative, you will obtain this expression. What does it mean? It means that this is the probability density function at beta 0 plus beta 1 x1 plus beta 2 x2 times beta 1. Okay, because of this, after you run the logical probit models, from the output you can obtain information only about the significance and only about the direct sign of the relationship, and that's all. Because this term is always positive. This is probability density function. This term is always positive. Because of this, the sign of this expression is determined by the sign of beta 1. Okay. And also you can say about the after you take the partial derivative of logit model. So again, you see this expression times beta 1. And again, it's not very convenient, of course, to try to interpret something from beta parameters, because instead of this, you need to find the marginal effects. Okay, and this is the marginal effect of probit model, and this is the general form of the marginal effect for logit model. If you want to interpret, let's say, beta 1 parameter in both cases. Okay, so what can you see from these expressions, from these final expressions? You can notice that the effect, the marginal effect, in both cases, in probit and in logit model, depends on the slope of the probit or logit model, but also depends on the values of x's, because in both cases, all the variables and all the outcomes of these variables are taken part in the estimation of marginal effects. What does it mean? It means that the interpretation and the size of marginal effect depends on X values, and we have different outcomes in X values. So what does it mean? Let's try to visualize this idea. Let's say that you have here, there's the curve. This is the probability curve, and on X and y-axis you can see the value of probability, and here is the let's say variable X. This is H. So how can we interpret the effect? The marginal effect means that if we increase X by 1 unit, we need to find the response independent variable in probability. So let's say that we increase by 1 unit from, let's say, minus 1.2 to minus 1. And you can see here that the response in the dependent variable in the probability will be rather small. But if you take another interval on this curve, let's say this one, yeah, and want to increase from 0 to 0.5. So you take the same 1 unit increase, yeah, but now your response in the dependent variable will be larger if you compare with the first case. So what does that mean? It means that it's the marginal effect in probit and in logit model depends on the value of X. This example is a very good illustration. Just we've done this, try to discuss using these expressions. Let's again take a look at them. Yeah, you can see that when you estimate the marginal effect, this is the result of your estimation in probit and logit models. You can see here that X variables are included in this expression in both cases. And so the marginal effect depends on the value of X. So the following question, how can we calculate the marginal effect? If any time we obtain the different values of the marginal effect. Let's say that we want to interpret, for example, variable gender, here sex, yeah? We have here only two outcomes, two categories, male and females in general case, yeah? And of course, we can calculate the marginal effect in each point, for each category. It will be, let's say, easily done if we compare with some other cases, with the continuous cases. But let's say that we have here a variable income or variable age. These variables are continuous, so we have many different cases for each variable. This is the continuous variables. So we can calculate the marginal effect at each point for the continuous variable income, yeah, or for the each point of the variable age. It will be too strange. We don't obtain any we can't obtain the answer on our research question if we just have a million values of marginal effects. We need to combine them in some way. So how can we do this? For this purpose, we have several solutions. So you remember from the previous seminar that when you apply the logit or probit models in Stata, you just run the command probit, then specify all your variables, or you just run the model logit and then specify all your variables. And you will see some output, some table, yeah, with the coefficients. So from this output, you can take a look only at the significance and the sign of the coefficients, and that's all. Next step, if you want to interpret the values of the effect of each factor on your probability on your dependent variable, in this case, what you need to do, just to apply the common margins and specify which type of margins. So, generally speaking, we have three options. We can calculate the first option, we can calculate the marginal effects at the mean values. So instead of obtaining a lot of million different values of marginal effect, let's take the mean value of X variables and plug in them in this expression. Yeah. So this is the first case. We can plug the average value of X1, for example, in the formula calculating marginal effects. So in this case, you will apply this expression. Here you can see that we don't need to plug in the million outcomes of the X variable. I mean, in the case of income, for example, yeah. You just need to find the mean value of income variable in your sample and plug in them in this expression, or in this expression. Okay. The second option, instead of marginal effect at the mean value, you can find the average marginal effect. It means that you calculate the average value of marginal effect across all your sample, and then find only one average or mean value of all that marginal effects. And also you have the third option. How can you do this? It means marginal effect at the representative value. The difference with the first and the second one, that you need to plug in here some custom values of X. For example, let's say that you have some sample, and in the sample you have variables, variable that contains information about the person's years of schooling. Also, you have information about the person's gender, and also you have information about the person's monthly income. And you need to find the probability, the same example, that the person owns a house. So you run the logit model, for example, or probit model, and then you want to find the marginal effect for specific respondent. Let's say for some average respondent that will be a female with 14 years of schooling and with income that equals 80 rubles per month, average income. So in this case, you can plug in this formula these specific values for x's. For example, or instead of x1, you plug in here that will be a female. Instead of x2, you plug in here that this female will have 14 years of schooling and so on. Okay, so the third option means that you plug in some custom values of x. So let's summarize. What does it mean? The idea behind the marginal effects very close to the estimates of the linear probability model. Again, you want to find how the change 1 unit increase in x variable change the value of your dependent variable. In our case, change the probability of being that our variable equals 1 or equals 0. What is a good news that you can interpret marginal effect in the same manner as you interpret the coefficients after the ordinal least squares method. The most popular option among three of them is the average marginal effect, but you can choose any one among these three. It depends only on your research question. It depends only on which effect you want to estimate. So it's up to you. But of course, I need to clarify that the marginal effects at mean and average marginal effects are more popular options than the last one. And of course, sometimes instead of just estimating some values, it will be more convenient to also add some charts, also add some graphs that describe your marginal effects. So let's take a look how can you do this in Stata. Here, as you can see, the table. In the first table, this is the linear probability model. So the first, not table, the first column describes the coefficient of, let's say, results after the ordinal least squares method, just as the example for comparison, okay? So here's our dependent variable. Let's say that the respondent owns a house, means y equals 1, otherwise y equals 0. And here you can see some variables like gender, education, and so on, okay? Second, third, fourth, and fifth columns here present the result after the margins comment. So here you can see the marginal effects. The abbreviation MEM here means marginal effect at the mean, this one. And the next column means average marginal effect. These two columns for probit models and these two columns for logit models. So let's compare. What do we have? In this example, we can see that most of the results are very similar to each other, even if we compare them with the linear probability model. So, for example, education, yeah, or gender or age, but H no. H is not very close if we compare linear probability model coefficients with the marginal effects. But all the marginal effects are very, the values of the marginal effects are very close to each other. Okay. So this is how you can present and how can you interpret the coefficients and the marginal effects of the after the logit model, after the logit and probit models. Okay. So of course, this is just an example. You don't need to use in the same research. I mean, your at least your research projects. You don't need to apply probit and logit answering the same research question. Please choose only probit or only logit. Of course, you can estimate several marginal effects. For example, this one and this one, both of them, and compare the results in the same, let's say, table as in this example. You can compare average marginal effect with the mean, with the marginal effect and the mean values. Okay. And you will see that the values of these effects will be almost the same. And of course, the sign, the significance will be the same. Okay. The interpretation of these values is almost the same as in the ordinary squares method, so it will not be a problem for you to interpret the results. Okay. But also, we want to visualize the marginal effects. So you have some special common sense data that can help you to visualize these values in nice histograms, not histograms, in nice graphs. For example, like this one, we take the age, variable age, and we want to visualize the effect of age on the probability to be, let's say, self-employed. Here's the example of self-employment. Okay. What does it mean? You can see this is the curve. Yeah. And if you compare the age group, let's say this age group from 20 to 30 years old with the more older people from 50s to 60s, people in their 50s years or in their 60 years are more likely to be self-employed than people in their 20s or 30s. I want to clarify that this data set, not from Russia, this data set from the United States of America. And this is not very new data. I think that this data from the beginning on 2000s. Okay, so maybe because of this, maybe now the picture a little bit different, but generally speaking, this is the example how can you visualize the marginal effect. You can use the common margins plot like in this case, and it will be very easy to interpret the effect. Okay. So you can add nice graphs to this to these tables with the marginal effects. Okay. And also, when you work with the logit and probit models, you can use interpretation of any effects only in the marginal effect terms. But logit model one more option. When you work with the logit model and only with the logit model, you can interpret your result not only in the marginal effects terms, but also in the odds ratio terms. I hope that some of the groups, or maybe even all the groups, practice in the seminars, how can you do this? So we discussed previous time that the odds ratio is just this fraction where you can see in the numerator probability that some event equals 1. For example, the person is self-employed, over the probability that some event equals 0, or in terms of self-employment, it means that the person is paid worker, for example, or otherwise. Yeah. So if you want to interpret after the logic model in the terms not of the marginal effects, but in the terms of odds ratios, you can add specific option after the logic model, or R option. Yeah, I think that the your teacher showed you how you can do this, and you obtain in the outcome table not the coefficients. You obtain in the outcome table the odds ratio. And the interpretation is not very complicated. So the interpretation in terms of odds ratio, first of all, you need to take a look at the 1. What does it mean? 1 value. So if you remember, when we work with the ordinal least squares method, one of the sign that the coefficient is significant, we need to take at the 0. Yeah, we compare with the 0 every time, with the 0 value. For example, if the 0 includes in the confidence interval, you remember that in this case, we say that our coefficient is not significant. In the odds ratio terms, we have the same logic, but instead of 0, we use 1. Why this value is 1, you can obviously see from this fraction. So in odds ratio terms, every time when we want to say something about the significance, or something about the direction of negative or positive effect we have, we need to take a look, we need to compare with the 1 value, how it looks like. So if you obtain odds ratio, and this odds ratio less than 1, it means it indicates decrease occurrence of an event. So it means negative effect, let's say, yeah, in general terms. If you obtain the value of odds ratio higher than 1, it indicates that you have a positive effect or increased occurrence of an event. And also, if you see that there are 95% confidence interval includes 1, it means that your effect is not significant. So absolutely the same logic when we use the 0 in the ordinal least squares method in the linear regression model. Okay. And the difference that, of course, we use logit, we use maximum likelihood estimation, and we owe our interpretation in terms of odds ratio. And again, odds ratio means here is this fraction, this ratio that we just discussed, okay? And probability, you remember, ranges from 0 to 1, but odds ratio, odds ranges from 0 to infinity. So you can see negative value of odds ratio. And a logarithm of odds ratio ranges from minus infinity to plus infinity. Please remember about this. And be very careful when you interpret. Remember that we compare every time with the 1. And Traditionally, odds ratio can be reported in the studies such as occupational health, medicine, health outcomes, and sometimes in some management and economic studies. But more traditional for economic and management studies and business studies to report not odds ratios, but to report marginal effects when you interpret the results, okay? So on this slide, you can find how, let's say, some hint, how can you interpret your results of odds ratio. And for example, if you will see in your table with the odds ratio that you have, let's say, value equals 2, and you have a binary independent variable, you can see, you can interpret this odds ratio that let's say that binary independent variable here is a gender, okay? 1 equals that the respondent is male, and 0 equals that the respondent is female. So it means that being male puts you at 2 times greater odds of being, let's say, self-employed, okay? Or you also can say like when being the male increase odds of dependent variable equals 1 are twice than the odds of being female after holding all other factors fixed. Okay. And when you have a continuous independent variable, in this case, interpretation also is similar. Let's say that we talk about the income, for example, yeah. Income is a continuous independent variable in our example, and we can say that for a 1 unit increase in income, the odds of our dependent variable being 1 versus 0, let's say, being 1 means to be to have a own house increase by a factor of 1.1, or in other terms, you can use this interpretation. If you see that the odds ratio of the continuous variable income equals 1.1, you can interpret this as the proportionate increase of 0.1 times the initial odds ratio. So the increase in X in income, for example, by each 1 unit increases, the odds of your dependent variable that you own the house by 10%. And that's all. Okay. You will have more practice during the seminars. So if you have any questions, please, in the interpretation, I mean, please ask your teachers or write me the letter. So now let's compare the results. Now let's combine in one table first the coefficients from the logit model, this coefficient that we can't interpret. Then in the second column, we present the values of marginal effects at the mean value. In the third column, we present the results of, again, marginal effect, but average marginal effect after the logit model. And in the last column, we add here the odds ratios. Okay. And now let's compare the results, okay? So what can you see? That the sign and statistical significance is the same in all columns. And because of this, you remember that if you just need to say something about the statistical significance and the effect, negative or positive effect of some factor on the probability, you can do this exactly after the logit model. But you can't interpret these coefficients after the logit model. Instead of this, we need to take a look at the second, third, or on the fourth column in this table. Now let's compare the second and the third column. You can see that the marginal effects in both cases are very similar. Yeah. The interpretation is almost the same as you interpret the coefficients after the linear probability model. And now let's take a look at the last column. This is the odds ratio. Again, let me remind you one more time that odds ratio interpretation can be used only after the logit model. You can't use ordinary odds ratio interpretation after the probit. It's impossible, okay? Because this is the different technique. So what can you see here? That, of course, the values here is not the same, but the interpretation in the last column will be in the terms of odds. Okay, the second and the third column we interpret in terms of probability. The first, here's dependent variable is logarithm of odds ratio, here is dependent variable's probability, here's the probability, and here the dependent variable is odds ratio. Okay, so what does it mean? It means if we how should I put it? If we coded our gender as 1 if the respondent is male and coded 0 otherwise, it means that being male puts you at 1.5 times greater odds of being, let's say, self-employed. Our dependent variables here, y is self-employed. Okay, again, let me repeat the same. Being a male puts the respondent at 1.5 times greater odds of being self-employed if we compare with the females, for example, holding all other factors fixed. And also, you can say, if we compare every time with the one value, yeah, it means that when the respondent is male, odds of being self-employed are bigger by 50% than for females. Okay. So after, oh, I think that we should stop here. Even 5 minutes before. So, okay, let's finalize this about the model diagnostic next time. But also, I want to remind you that that next time you will have the test, okay, on Tuesday. And this test will be online in Microsoft Teams, okay? And you can find the demo version of this test in LMS, not of this test, some example, yeah, of the test in LMS and in the program, in the syllabus of our course, okay? This is just an example. You will have some outputs from data, and you need to interpret some, let's say, something, some result of the test, some results of models, and answer some questions. All the questions will be open questions, so you need to write some interpretations, you will need to provide some ideas and answer some questions. And also, I want to note that you need to be prepared to answer the questions that concerns all our course, not only ordinal least squares method, but also logit and probit models. Okay, so the output could be from any type of the discussed models, and there could be any questions. Okay, do you have any question on this lecture or about the test? Georgi, I see that you don't have any questions.
So will we have the interpretation of today's current topic also? Yes.
Yep.
Great, thank you.
So you will have one more seminar on today's topic about the logit and probit models. So if you have any questions, please ask your teachers during the seminars, okay? Be prepared. And again, if you want to prepare what you will see in the test, please check the demo version of the test, because you will see exactly some outputs. It could be outputs from the regression, it could be outputs from different tests that you discussed during the seminars and that we discussed during the lectures. Please be prepared that these tests will not be surprise for you. Okay, when will be the when you will need to submit the final projects? I will write you the letter, but I think that this date will be the 10th of June. Okay, so you will have less than 1 month to be prepared. So first of all, you need to submit your reports and do files, and after this you will have some time for prepare your presentation. Because you will not need to submit the presentations, you will have some extra days to prepare them. Okay, any other questions? Sorry that we delayed for 10 minutes. Okay, but remember, if you have any questions, please write me the letter. Okay, see you next Tuesday if you don't have any other questions.
Excuse me, I have a question about the project. Is it okay to ask now or maybe?
Of course. It's up to you. So if you want to have a personal conversation, we can just call right now after the lecture, for example.
Okay, maybe I just write the letter, I think.
Oh, you can just write me a message in Teams.
Okay, okay, thank you for the lecture. Goodbye.
Thank you. See you. Bye-bye.
Thank you. Goodbye.
Thank you
Bye-bye.
for the lecture. Goodbye.
Bye.